Hello everyone, Namaste. I am Ramnath who would like to share with you some information on the VLSI design topic, probability density and its impact on design yield. This is part 3. Part 1 and 2 are already shared. One more part is awaited. Please feel free to provide your comments or any suggestions. Thank you so much. Have a good day. Variation is part of Mother Nature and the distributions of the random variables will affect the statistics, mean, standard deviation, etc. So this is the general form of distribution of the probability density function fx, and here mu represents the mean and sigma represents the standard deviation. Here this is a very general distribution function. So the fx and x distributions can be any one of these. However, and these are all part of the actual distributions of some random variables. Say, for example, pole in some specific state, or the distribution of COVID in a specific scenario, or the bacteria growth in a specific area of the body. Like that, all these are all distributions. So to know, but to analyze these specific, these unique distributions is somewhat that like an involved process. So in most of the simplistic considerations, we consider the normal distribution. Normal distribution means, like here in this specific general distribution, we consider mu equal to 0, mu to be 0 and the sigma to be 1. So this density function becomes a simplistic one here, because sigma became 1, mu became 0. So this is the new function, and this function represents in this fashion, and here it is mu equal to 0 and sigma equal to 1. So that is how the things will be represented here. So then most of the times, if we analyze this one, then it will be easy to get the main concepts. Okay, so we will be able to figure out. But however, to specifically figure out the unique scenario, then we need to take the actual general distribution function, and based on the specific random variables, we need to figure out the specific density function. Design hold or MPW timing convergence or critical care product leakage power consideration, etc. should be met based on customer use case situations as driving constraints, because these are all very critical metrics. However, at times some products are designed considering Six Sigma as the design constraint, since it is believed to represent 3.4 parts per million DPMO. Definitely, if the whole involved items in the chain are complying to Six Sigma, it is acceptable to allow even this metric also to be meeting. So we need to evaluate what is Six Sigma and when it translates to 3.4 parts per million. Okay, so if you see here, the Six Sigma corresponds to the past situations which are related to DPMO of 0.002. So this is the actual DPMO value 0.002 as seen here. However, note that there is a situation wherein if a Six Sigma process is not continuously tuned over a long time, then the Six Sigma process would move 1.5 sigma on either side from the mean. This is a very crucial statement. That means like somebody is not maintaining the process, whether it is a manufacturing process or the materials delivery or the design implementation process. Any of these, if one is not maintaining, then definitely it will slowly drift away. So there is a possibility that over a long time it can drift by 1.5 sigma. Assume that in a sawmill, the one is not maintaining the sharpness of the saw. Assume over a period of 1 year or 2 years down the lane, then the sharpness of the saw will differ from the earlier original situation. So that is what is being considered here. So let us see what is meant by shifting by 1.5 sigma. So what it means is, see, if you see here, the mean is represented properly and by the blue curve, and that is spread uniformly. Currently we are considering the normal distribution curve as considered here, and it is having a spread from -3 sigma to +3 sigma. Mean is at 0. So now if you consider the other situation, because of the drift, it is now shifted by 1.5 sigma to the right. It can also drift to the left also, because the process is stable. If there is a situation like this, then you will have the DPMO as 3.4 parts per million instead of 0.002 parts per million. 0.002 translates to 2 parts per billion. So if that process is stable, then the 6 sigma plus or minus 6 sigma yield a DPMO of 2 parts per billion, and we will evaluate whether this statement that 6 sigma is plus or minus 6 sigma is correct or not. We will figure out how closely the semiconductor manufacturing process steps are controlled and maintained. So if you observe, the semiconductor metrology instruments are designed for wafer inline inspection for the management of the semiconductor manufacturing process. Why they are doing all this? Because you cannot control something that you don't measure. That means, like, as we know, there are many micro elements such as the pitch, width, concentricity, fin height. All these things are very important, whether it is a planar transistor or a FinFET. So in all these things we need to first measure them. Then only we will know where they are. Then only we can take additional steps in bringing back to the mean situation. Okay, so many of the devices and metrology systems use a combination of laser, optical and electron beam technologies to help improve the quality. There are around 400 to 600 steps in the overall manufacturing at critical points. These semiconductor metrology instruments monitor the features, as I mentioned, the space, pitch, roundness, sidewall angle and all. How do they do that? For that they employ different instruments. Most of the important ones are wafer probers, ellipsometers, CD SEMs, reflectometers, etc. And here I'll briefly discuss a few of them. Here a wafer prober is used to test a semiconductor wafer. before it is separated into individual dies. An ellipsometer determines the properties and surfaces of thin films by measuring material characteristics such as layer thickness, optical constants, or surface roughness. CD-SEM, CD stands for critical dimension, SEM stands for scanning electron microscope. It uses a focused beam of electrons to generate a magnified image of the structure. That is for measuring the critical dimensions, whatever are listed here. So all these things need a revenue, need money. So you know that the semiconductor metrology industry market cap is $7.5 billion in 2022. And at the same time, the semiconductor industry market is close to $550 billion. So you should know that this much industry is behind to ensure that the process is monitored and kept at a certain level of quality. Using the semiconductor metrology instruments and the associated flow and processes, the statistical process control will be followed to achieve high controllability. Control charts is a widely used tool for process monitoring in the semiconductor industry. By polling the sample design metric, for example IDS or VTH or line pitch or concentricity, these things need to be measured at regular intervals or in specific samples. So control limits define the boundaries of the normal behavior of the process. Control limits are therefore independent of specification limits. The probability of getting points outside the plus or minus 3 sigma range is very low. So that means like if this is the mean and this is the sigma, the control limit, LCL, lower control limit and upper control limit are defined in this way. And if you see here the IDS value, this can be any design metric, and here for simplicity taken the drain source current. So here these are all the different values the IDS has taken for a period of time, but regular intervals assume that these values are sampled. Then you will observe that there is a distribution around this, and the upper value will be so and so and the lower value is so and so. So the mean is here. So the mean is well within the 3 sigma level. So the LCL and UCL are well within the 3 sigma of the mean. So on top of this, what we would like to know is the USL and LSL. LSL stands for lower specification limit, which is dictated by the customer. USL stands for upper specification limit dictated by the customer. That should be in this way. That means like USL should be greater than UCL and LSL should be less than LCL. So in that way it needs to be. So when this is ensured, the process capability CP refers to the ability of a process to meet customer requirements or specification limits, means how consistent its output is being within its lower and upper specification limits. So between USL and LSL, how closely this process is, that is mentioned by the process capability. So if there is a process which is going out of the 3 sigma range, that means like towards the USL or towards the LSL, that means like that has some problem. So immediately one should take care of it, because it is being measured and being observed so carefully that the associated process people and the corresponding designer should be able to fix the issue. Let us consider some more details on the process capability. So here, let us take one small example wherein the target value is 100 microamps for an IDS drain to source current design metric, and these are the time at which it is sampled. So this is how the drain to source current is varying. So this is the upper specification limit mentioned by the customer. That value is 106, and the lower specification limit is mentioned as 94 microamps. So this is how the process is varying. So by considering this process, you will observe that the mu and the sigma of this orange line is 94, 98 and 1.03 microamps, mu and sigma. So if you use the process capability equation USL minus LSL by 6 sigma, the reason why they taken 6 sigma is it is at the most it should go plus or minus plus 3 sigma or minus 3 sigma. Definitely it should not be well past it. So they have considered that it should be well within this. So the process capability is equation is derived in that way. So USL minus LSL by 6 sigma, if you observe, it is 106 minus 94 by so and so. So the value is 1.94. There is a catch here. Here this seems to be correct as long as the process is within this. However, not every time this process capability will give the right situation. Okay, assume that the mu now has become 198.94 instead of 98.94 earlier. So the mu is here, sigma is exactly same. Assume that it is varying exactly as before here. So it is exactly same, mu has increased. Now if you observe if you calculate the same CP, it will result in the same value as 1.94. If it is 1.94, it is a very good value actually. But you know that this is a bad situation because it is way above USL, way above LSL. So this is not the right representation because it is already out of the range. So we need to have another metric because it does not take the impact of mu. So to take the impact of mu, there is one more parameter is included to monitor the process, that is CPK, which is the minimum of USL minus mu by 3 sigma or mu minus LSL by 3 sigma. Any of these, minimum of it. So if you calculate in this way, by using the same previous values, you will observe that CPK is coming out to be 1.6, which is a very good and true representative of the process. So even if the process goes out of the range, it still will be able to predict the CPK properly because it is considering the minimum of these values. So CPK represents the process capability index or ratio, which measures how centered the data is. Okay. And most semiconductor companies target a CPK of 1.67 for their processes, although some would be satisfied to have an actual CPK of 1.33. That is how the process is ensured to be well within the limits of plus or minus 3 sigma, and whichever is going past the plus or minus 3 sigma will be rectified because it is continuously monitored by the semiconductor metrology instruments. Hence earlier hypothesis that a process could swing by more than 1.5 sigma is not quite reasonable. One should evaluate that. Hence, plus or minus 6 sigma of which represents a DPMO of 3.4 is not reasonable. Hence, it does plus or minus 6 sigma will yield more or less 0.002. For a normal distribution where sigma ranges and past situations yield values, DPMO is in this fashion. Then the associated process capability is also mentioned in this way, and its values are 0.33, 0.67 in this way. And since we know that process capability is not the right indicator, so we will have to use CPK, and these values remain as before.